welcome back for the second part of this morning session. We are very happy to have N.Leopold, and he's going to talk about the derivation of the Landau-Pekan equations in a many-body mean field limit. So, thank you very much for the introduction, and also thank you, Marcello and Chiara, for the opportunity to give a talk at this great conference. I would like to talk about the derivation of the Landau-Pekan equations in a mean field limit, and this is the talk is based on joint work we started with Puskas and Seilinger, and it can be found under the following reference bar on the archive. And the outline of the talk is as follows. First, I would like to introduce the models, which were already introduced by Robert on Wednesday, namely the Fröhlich model and the Landau-Pekan equations. Then I would like to state our main results, make a comparison with the literature, and if time permits, give a sketch of the proof. So let's start with the Fröhlich model. It was originally introduced in 1937 by Herbert Fröhlich to describe an electron in an ionic crystal. However, it can also be used to model Bose-Einstein condensates, which has an interaction which effectively behaves like an interaction which is modeled by a phonon field. And if we look at the model, we see that we have the Hilbert space L2 over R3n, which describes n particles, and then the bosonic Fock space over L2, which describes the excitations of the phonon field. And an element in this Hilbert space evolves according to the Schrödinger equation with the Fröhlich Hamiltonian. And the Fröhlich Hamiltonian has a kinetic part. It has a field energy, which is just a number operator, because in this model, the phonons have constant dispersion. And then one has a coupling term to the phonon field with a coupling constant square root of alpha, which is, so to say, a quantum field where the A and A star satisfy the usual commutation relations. And then one has this form factor Gx of k, which scales like 1 over k. And in general, one must be a bit careful because it's not an L2. However, the Hamiltonian can always be defined via the associated quadratic form and also the time evolution. So in this model, one expects classical behavior at least in two situations. And one is if we fix one particle and let it couple strongly, so to say, to the phonon field. And this then describes an electron in an ionic crystal, and was the situation Robert has talked about on Wednesday. However, one also expects classical behavior if one has a Bose-Einstein condensate of many particles which weakly couple to the phonon field. And in both situations, it is expected, so to say, that the condensate wave function and the classical field evolve according to the Landau-Pekan equations. However, I would like to point out that also both times the effective equations are the Landau-Pekan equations. The emergence of classical radiation, so to say, happens because of two different mechanisms. Because in the first situation, it's rather because the electron decouples because of this adiabatic decoupling from the phonon field. While in the second situation, it is more the case that one has a lot of particles in the same state which simultaneously create phonons. And in this talk, I would be interested in the second situation. So I look at bosons. So I look at the Hilbert space L2s of R3n, fix the coupling constant to be 1 over square root of n, and want to consider the large n limit. And the scaling is chosen, so to say, that all terms are of the same order. So on times of order 1, one really sees the creation of phonons, and then one also wants to see that they behave. And next, it was partially also already introduced by Robert, but I would like to give a short motivation in which situations one thinks that the phonon field behaves classically. And a central role in this context is played by coherent states, which can be generated if one acts with the while operator on the vacuum. And the while operator is a unitary operator with, which satisfies the following shifting property.
And because of the shifting property, if we, for example, look at a state where all the particles are in the same state, but that's not so important for the moment, and where the phonons are in a coherent state with mean particle number n, then we can act with the scaled annihilation operator on the state, and with scaled, I mean I multiply it with a factor of n to 1/2. And if one then uses the shifting property and also the fact that if the annihilation operator acts in the vacuum, one sees that coherent states are eigenstates of the annihilation operator. So this action here of the scaled annihilation operator can just be replaced by a complex number. However, there are no eigenstates of the creation operator. However, if we let act a scaled creation operator on a coherent state with high occupation number, so to say, it is kind of an approximate eigenstate, because we see that we get the complex conjugate of phi k, and then an error which is of order n to the -1/2, which arises from the quantum fluctuations. So if we then the quantum field from the first slide let act on the state, so to say, we can replace the annihilation and creation operators by a complex number, and in this sense approximate the quantum field by a classical field. So this raises the question if this structure of the state is preserved during the time evolution, because then we could at each time step, so to say, replace the quantum field and get a description by means of a classical field. And if one formally assumes that this holds during the time evolution, one can, for example, look at the Ehrenfest equations to see that the dynamics of this function psi and phi should be given by the Landau-Pekan equations. And this were also already introduced on Wednesday. I just give a short recall. So in our setting, it describes the interaction between the condensate wave function and the classical phonon field. And if we look, so to say, at the equation, we see that the condensate wave function satisfies some Schrödinger equation with a classical field. And the mode function of the classical field has two terms, where the first term ensures that the free field behaves on each side like a harmonic oscillator. And the second term is a coupling to the density of the condensate wave function. So we see that the condensate wave function interacts with the classical field, and the classical field has as a source term the density of the condensate wave function. So this is a nonlinear equation. However, I would like to point out that in the scaling here, we don't have this factor of alpha squared here, like in the strong coupling limit. And therefore, these equations don't have this adiabatic nature, which happens because of the separation of the time scales. The space L12 denotes a weighted Sobolev norm, and we will use, so to say, that these equations are well posed in the state H2 L12, which was shown in a paper by Rupert Frank and Sui Gan about the strong coupling polar. Okay, next I would like to present our results, and I would like to start with the most simple one, and therefore I recall the definition of the one particle reduced density matrix, which was already introduced in the talk before. But since we now, so to say, have particles and a Fock space, we have to look at the projector on the many-body state and trace out the Fock space and the degrees of all particles except of the first one. Then I would like to consider initial states where psi naught phi naught is in H2 L12, and a many-body state, which is, so to say, a condensate and a coherent state with mean particle number n. So if we then evolve the states according to the Landau-Pekan equations and the dynamics of the Fröhlich-Hamiltonian, we can show that at later times, the one particle reduced density matrix of the particles converges in the limit of large n to the projector onto the condensate wave function. So one sees that the condensate is stable during the time evolution and can effectively be described by the Landau-Pekan equations. And what one can moreover see is, so if we look at the many-body state and we destroy the coherent state of square root of n phi t, then we can, so to say, look how many excitations are above this coherent state. And then we see that these excitations are of lower order than of order n. So this square root is just comes in for technical reasons, but still one sees, so to say, that the excitations are of lower order. In general, this result holds for a larger class of initial states where the many-body states are all in the domain of the free Hamiltonian. However, I would not like to talk about this more general result now, but I would like to talk about a bit different result, which is about many-body states which are in the domain of the Fröhlich Hamiltonian. So again, I look at psi naught phi naught, which is an H2 L12, and now on a generic many-body state, which is in the domain of the Fröhlich Hamiltonian, such that the energy per particle is finite for all n. Again, we evolve the states according to the two dynamics, and then we can show that we can approximate the left-hand sides if this value dn is converges to 0 if n goes to infinity. And this value dn consists of three functionals in which we insert the initial states. And the first functional, just so to say, says that the particles are in a Bose-Einstein condensate. The second functional says that the phonons are in a coherent state. And the third functional says that the fluctuations around the energy per particle are small. And it is, so this third functional restricts, so to say, the states onto a subclass of states where the variance of the energy is small, and this is needed to control the ultraviolet behavior of the phonon field. And if one, for example, looks at the model with an ultraviolet cutoff, the same statement would hold true without the appearance of C of psi and naught. However, then one would have like a dependence of the cutoff parameter on the right-hand side. And so I want to further elaborate a bit on this. Namely, so we have to go in the domain of the Fröhlich Hamiltonian because of the appearance of this C psi and naught. And with this respect, it's interesting to note, like also Robert pointed out, that the domain of the Fröhlich Hamiltonian and of the free Hamiltonian only have the unit vector in common. This has been shown and is nicely explained in a paper by Marcel Griesemer and Andreas Wünsch. And as I've already said, so to say, the main technical difficulty also in comparison to earlier works is this ultraviolet behavior of the interaction. And in order to overcome this, so to say, we introduce a measure of condensation or coherence, which involves the cross transform. And we moreover then use a representation of the Fröhlich Hamiltonian by means of the cross transform, which is kind of a multi-particle generalization of the result by Marcel Griesemer and Andreas Wünsch, but which, so to say, in our setting, the proof goes exactly along the lines. And in order then to control the interaction between the phonons and the particles which are not in the condensate, we need the variance of the energy per particle. And in order, so to say, to control this, we use the symmetry of the wave function and estimates, which are similar to a former work of Peter Pickel and myself about the derivation of the Maxwell-Schrödinger equations. However, to apply it in this setting, we then also need an operator bound, which was proven in a paper by Rupert Frank and Benjamin Schlein about the strong coupling polar role. Okay, so next I would like to give a short comparison with the literature. So the closest work to ours is the one by Siad Amari and Marco Falconi, in which they derived the Schrödinger-Klein-Gordon equations from the renormalized Nelson model. However, this is a bit different from a technical point of view because it uses a Wigner measure approach. From a technical point of view, I would say the work of Marco Falconi with the coherent state approach, or works of Peter Pickel and myself about the derivation of the Maxwell-Schrödinger equations, are the most similar ones. And one can also, in a sense, place this result in a larger context and ask, when do quantum fields behave like classical fields? And then This situation also appears in the strong coupling limit, about which Robert talked on Wednesday. However, it also appears if one has a fixed number of particles which couple to a quantum field with high occupation number. This is usually called a partially classical limit and has in the last years mostly been considered by Michele Correggi, Marco Falconi, and Marco Olivieri. Sometimes it's also possible to approximate a quantum field by a direct two-particle interaction. Okay, so I don't know how much more. Okay, right. That's great, because then I can, so to say, try to explain a bit what the cross transform is. So the cross transform is defined via this function bkx k. So for values of small k which are bigger than capital K, it stays like 1 over k to the third and has this factor of e to the minus ikx. And the cross transform in our setting, so to say, we then define as the sum over all bkj, and then we scale it with 1 over square root of n. And since this bkj are the coordinates of the particles, we see that the cross transform creates correlations between the particles and the phonons. And in order to see how this, so to say, happens, it is instructive to apply the cross transform to the Fröhlich Hamiltonian. So if one applies formally the cross transform to the Fröhlich Hamiltonian, one gets the cross transform Fröhlich Hamiltonian, which is the sum of 3 operators. And the first part is just, so if we look at it, this is just the original Fröhlich Hamiltonian, because phi just stands for A and A star. So we see that we again have a form factor which decays like 1 over k, but now we have a cutoff in the ultraviolet modes. And then the other important term is the second term. There we see we have annihilation and creation operators, and here we have k times bk, so we have a decay of 1 over k squared. So in a sense, the cross transform replaces the ultraviolet modes of the interaction by some ultraviolet modes which have a better behavior. However, the price to pay is that now a gradient appears in front and below the creation and annihilation operators. So roughly speaking, one can say that the cross transform uses the regularity of the electron to smoothen out the interaction. And next, I would like to talk about the result of Master Giesemann and Andreas Wünsch, which we had to, so to say, extend to the many particle setting, but this is exactly along the same lines. So if one chooses some k in the cross transform, which is bigger than some k tilde, one can show, so to say, that the Fröhlich Hamiltonian is represented by the cross transformed cross Hamiltonian. And one can moreover use the cross transform to relate the domain of the free Hamiltonian and the Fröhlich Hamiltonian. And for us in our setting, it was necessary, and this is really important, that this k tilde does not depend in a non-trivial way on n, because it allows us to tune it later in the derivation and to let this cutoff grow with the particle number. And how we then prove the second result is that we define a functional, and the first functional, so to say, measures the excitations in the state u cape psi and t above the condensate. So we project onto the orthogonal complement of the condensate wave function. And the second functional, so to say, measures the excitations above the coherent state. And the third functional is just the variance of the energy per particle. And then, like one usually does in this business, we do a Grünwald estimate for this functional. And then we see that the optimal choice of k is the case if we let k grow like square root of n. However, now in our second theorem, we had statements.
The beta c, right?
Is it independent of time? Because it's
yes, this is independent of time.
Okay.
Since energy is conserved, it's independent of time. And now, so to say, for our second statement, we have to relate this functional to the reduced density matrices and the fluctuations of the coherent state. And there one can first use a standard result, so to say, to relate beta A to the one particle reduced density matrix of UK and psi and T. But the actual result was about the reduced density matrix of psi n. But then one can, so to say, use that the cross transform converges in the limit to the identity. And so if we look at the one particle reduced density matrix and the excitations about the coherent state, we basically only consider one particle. And then on one particle, so if we only consider the correlations between the first particle and the phonon field, then this, so to say, also go to 0, since we scale k like square root of n. And this we then can use to relate, so to say, the one particle reduced density matrix of psi n to the one particle reduced density matrix of the cross transformed state. Yes. So the cross transform only has a negligible effect on the level of reduced densities. So one could ask, why do we then actually introduce it? And the reason is that the cross transform effectively regularizes the interaction, because if we look at the time evolution of the cross transformed state, we just, so to say, see that it's generated by the cross transformed Fröhlich-Hamiltonian. And in this sense, I would say from a technical point of view, the insertion of the correlations by means of the cross transforms is very similar, but has a similar role as the Bogoliubov transformation in the derivation of the Gross-Pitaevsky equation. And I put here 2 of the earlier works, but of course it appears in many other works. So if time permits, I can also show the most difficult term to estimate. And here, since one has here the projector onto the orthogonal complement of the condensate wave function, one can interpret this.
Just stay on the other side of it because of the camera. Where it's jumping.
If you want to point, it's better if you point.
Okay. So one can interpret this term here, so to say, as the interaction of a particle outside the condensate with the phonon field. And we have here this cutoff parameter k, because, so to say, we inserted in the functional the cross transform. And the problem now comes from this form factor 1 over k, because if we, so to say, roughly think of, we do Cauchy-Schwarz inequality, we have one q, so we get a square root of beta a. And then, so to say, we get a square root, since we have here the difference of the classical part and the annihilation operator, we can estimate it by beta b. However, then always the L2 norm of the form factor enters. And since this is not an L2, so to say, the bound grows like k and would be not good enough to so to say, close the argument. And I think the most obvious thing what then could try would be to use the commutator method by Lieb and Yamazaki. So one could try to get a better decay, so one gets a decay of 1 over k more if one writes the exponential as the commutator with the gradient. Then one can do partial integration with the gradient and, so to say, apply Cauchy-Schwarz inequality. However, since the gradient acts on the first particle, we then get a term which goes like the gradient of the first particle q1 and the state. And this, so to say, quantity is difficult to control because it somehow is equivalent to control the kinetic energy of the particles, not in the condensate. And then we tried to get a way out of this. And the idea is to use kind of the symmetry of the wave function and then this estimates which are similar to this previous work. So to get a bound, not with respect to Q1 psi n, but with respect to to the gradient in the second particle and Q1. And in order to establish this in the setting, we need kind of I would say it's kind of a Lieb-Yamazaki bound from this previous paper by Rupert Frank and Benjamin Schneider. And the point is now that since we now have the gradient in the second particle, one can relate this last term to the variance of the energy, and in the sense close the argument if we restrict on this subspace. And so this then enables us to derive the second result. And since the cross transform converges in norm to the identity, we can then use this to get the first result. This is all I wanted to say, and thank you very much for your attention.
Thank you very much. So, questions? Line. Last one. So, can you also include a potential between the bosons? So, I don't know, some mean field potential additionally to the interaction through the phonon field.
Yes, I mean, this would be no problem. Because I mean, usually the interaction, if one does this Grünwald estimate, it just enters linearly. So one could then just estimate this. I mean, if the potential is positive for sure, because with this variance of the energy bounds, one has to be a bit careful, but also if it's, so to say, relatively bounded, then it should be no problem.
There are no more questions. Thank you, Nikolai, again. Switch to the second part, so maybe just 1 or 2 minutes for the